seminar, and one can see that the number of participants is higher than usual, but so I should, no. You don't have to so this is probably due to the fact that our speaker today is Tyrrell Rockafellar. Probably all of you know enough about him, so I will not make a formal presentation. And Terry will speak about stochastic variation inequalities in a dynamical framework. So, Terry.
Thank you. Some of you were at the tutorial I gave yesterday, which provided some background for this, more extended background, but some of you were not. So the very beginning will have a small amount of overlap with what I said yesterday. In both cases, it's concerning stochastic variational inequalities. And I guess you understand I was originally set up to give this lecture, but then it fell upon me also to give the tutorial, so I tried to work them out together to integrate them in a certain degree. So I begin again by reminding you what a variational inequality is. And of course, here we're going to be interested in variational inequalities that have stochastic ingredients in some sense. And I have to explain what that will mean. But the typical applications of variational inequalities are conditions for optimality or equilibrium. And they could be in a finite dimensional space, but also infinite dimensional. And it's good to have them be in a Hilbert space, even though people think about that usually as an infinite dimensional context. It's important even in finite dimensions because of probability theory. We can use an inner product based on expectations, even in finite dimensional spaces. So I will start from the beginning here with a Hilbert space. And I have in that space, there's nothing stochastic at the beginning. I have a non-empty closed convex set, and I have a mapping from the Hilbert space into itself, which I'm going to assume to be continuous. There are many variations on all this that could be developed, but I try to get across basic ideas here rather than a lot of technical details. So the idea of a variational inequality is to find a point of x at which the mapping F has a certain relationship to the normal cone to C at x. And the definition of the normal cone is given by certain inequalities. So it's common for people to write the variational inequality condition in terms of a system of inequalities, as you see here in red in the middle of this slide. But I think it's a big handicap to do this. I think it's very important to focus on the geometry of the normal cone, because otherwise you won't see the calculus and the modularity and all the things that can be done with variational inequalities on a modeling basis. So the variational inequality expresses the fact that minus this f of x should be normal to the set C at the point x. And this means that it could be, if you take the hyperspace, the half space, the closed half space with this vector minus x as its normal, then you will have a supporting half space to the convex set at this point. And all the vectors that give you such supporting half spaces are called the normals, and also the zero vector is included as a normal as a special degenerate case. Now in the theory of variational inequalities, you already see some convexity, namely the set C. It's possible, by the way, to take a non-convex set and write down the normals to it and pursue this, but this is a subject that not many people have really worked on. And it can be done in many ways. But another aspect of convexity comes into a typical assumption made on a variational inequality, namely that it be a monotone variational inequality. And monotonicity, this is in the sense of George Minty, who developed that concept back in the 1960s, refers to this inequality in red down at the bottom. If I take two inputs and two outputs and look at this difference, then the product should always be non-negative. Now, monotonicity is a bit unfortunate name because it has many other things, like it could relate to some order. This kind of monotonicity generalizes the concept of positive semi-definiteness of a matrix. It doesn't generalize monotonicity in the sense of order. Maybe it would be better if everybody called it minty monotonicity or something, but people don't, so we're just stuck with it. Now, it's important to have the idea of a maximal monotone mapping, which is one which cannot be extended. Its graph cannot be extended without getting something that would be non-monotone. So this is just the basic idea of a variational inequality without any kind of stochastics. And what we are going to do is introduce these things with stochastics, but I feel it's important to review briefly at the beginning why we're interested in variational inequalities, because it motivates what we will demand of a stochastic variational inequality. So one idea, in line with elementary optimality conditions, would be if you're going to minimize a smooth function over this convex set C, then this condition that I drew in the picture, which I repeated here with a gradient, this gradient condition is the first order optimality condition in that optimization problem. So this is a variational inequality in which the mapping F is a gradient mapping. There's another class of variational inequalities which is not quite so simple, and I like to call them Lagrangian variational inequalities. And in those ones we have a product of two closed convex sets, y and z. And we have a function on this product, and we're looking at this condition in which you see the first part looks like a variational inequality. For fixed z, it would be a variational inequality in y. And the second part is blue, is like a variational inequality in z, but you notice the minus sign isn't there. And I call this a Lagrangian variational inequality because it covers things like Lagrange multiplier conditions for this elementary optimization if we introduce Lagrange multipliers. But it's also actually a variational inequality as an illustration of how we can put variational inequality together from various pieces. If I take X to be the pair y, z, I take C to be the product set, y times z, and I take F to be this sort of, it's not exactly a gradient because there's a minus in one and not in the other. If I take F to be that mapping, then the variational inequality for that mapping is exactly the same as this blue condition. In particular, in nonlinear programming, you can put Karush-Kuhn-Tucker constraints into this picture. But also, you could also view this as a saddle point condition in a two-person game where one player is minimizing in y over big Y, and the other player is maximizing in Z over big Z, and you'll get these same conditions. So this is a Lagrangian variational inequality. Then I want to mention, before I get into the stochastics, a game-type equilibrium where we have a finite number of agents. Each agent has a strategy set, an independent strategy set. Again, all this can be generalized. The strategy sets can be dependent and so forth. And each agent wants to minimize a certain thing, but this thing is affected by what the other agents do, and that's represented by this traditional game notation. X minus I stands for what all the other agents beyond agent Y are doing. And then you have a similar kind of equilibrium. It's similar to the Lagrangian variational inequality in that you have a collection of independent conditions, one for each agent that represents the first order optimality condition for that agent. And I'm thinking here about stationarity as a better representation than global optimality. And then we can put these all together as a single variational inequality by taking the product set and defining a particular mapping. So these are some of the major applications. So when I get to a stochastic variational inequality, I would like it to be able to cover some models like this, but ones which naturally involve stochastics and therefore some sort of dynamics in time. So let's get to that right away. So I want to have a sort of a dynamical setting in which there's some intermixture in finite time. It would be nice to do these things in continuous time, but nobody really knows how to cope with all the technicalities of that at the same time. How to do because you already have infinite dimensionality often coming in terms of probability, and then to do that in time and everything too is a bit overpowering for most people, in particular me. But let's imagine that anyway as discrete time, in which we have a finite sequence of stages. It's not really good to call these stages because sometimes they're completely different. Like there's a decision we make today about building the shopping center, and a decision we make tomorrow about expanding it or remodeling it or something like that. They can be completely different, and they don't necessarily fit into a time frame. Or we could be building a portfolio today, and then a lot of time will go by before we make an adjustment to the portfolio. So these are stages rather than time periods. But the idea is that we want to consider a pattern where we make a decision. Then there will be some kind of information revealed as, let's just call it an observation. And then we're able to make another decision, a recourse decision, that reacts to that observation, but it's affected by what happened before. Then there's another observation, and we could imagine this process continuing, and for simplicity here, consistency of notation, I add a final observation, but it's just as easy to trivialize this. And the final observation is trivial. It's just as a notational troubles with all these things, how you're going to do that. But you don't need a final. You can or you may, whatever. Don't have a final observation. And now then I want to think of x as a vector giving all these decisions. And I want to think of C as this vector giving all these observations. And I want to think of the observations coming, they're elements of a set C, K, at stage K. And then the observations I have will be some elements of the product set. And then I want to think of each of these C's as a scenario. That's a common word used in this kind of subject. A scenario. Now the whole issue here with the structure with emerging information is the interplay between decisions and information, and that's comes into this English word which is difficult to pronounce, nonanticipativity. Nonanticipativity of decisions. They can't anticipate the future. They can't act on the basis of future information that they don't have. They can't anticipate. So it means that the decision made in xk can only respond as a recourse to the information accumulated up to that, but not to any future information that's not yet revealed. And so this would mean that my decision is going to have to be whatever I'm doing in this. I don't have an optimization problem yet, but the elements, the decision elements in it, whatever it will be, are going to be functions. They're going to be functions in which the first component doesn't depend on any information. The second can depend on the first observation, and so forth like that. That's the pattern of functions. And I'm going to simplify here by assuming that there are only finitely many scenarios, and each has a positive probability. So that means I'm turning my scenario space into a simple, discrete probability space. Obviously, there's a lot of room to go in this, but it involves a lot of technicalities which are hard to fit into a slide, and the basic ideas are the most important things here anyway. So this is my decision and observation structure. Now, what are we going to do here about setting this up for the formulation of optimization? And I could already set up an optimization problem in this setting, but I need to go further because of, well, the methodology I'm going to reveal. So what I'm going to do sounds at first, it looks a little bizarre. Instead of just limiting myself to those functions I know I need with that particular structure, I'm going to look at those within a much larger space, the space of all possible functions, response functions, without the limitation of non-anticipativity, because I want to introduce that limitation as a constraint which will be able to have a multiplier. And I need a larger space to achieve that goal. So I look at the space L of all functions, from the scenarios to these vectors, and allowing the first decision to depend on the future and so forth, and this as the larger space. And in this space, I introduce the inner product of expectation type. It's a perfectly good inner product, and that gives us a Hilbert space structure. And I could, of course, revert everything to Euclidean spaces. I could take each one of these functions and write it out for each xi. I have a vector for each xi. I could number the elements xi because it's finitely numbered. Could make this to be a giant vector, which would be an element of some Euclidean space, and I could use the Euclidean inner product in that space. But the advantage of introducing the expectation inner product is then you will get things like projections which correspond to conditional expectations. You are able to integrate into the probabilistic ideas. So in this big space now, as I say, I want this constraint. So I want to restrict myself to the functions in the bigger space that are the most important. So I'm going to introduce this nonanticipativity subspace. So if I think of a scenario as going up to k minus 1, then k and so forth on to the end, I want to look at these functions in the larger sense in which the component k only depends on the observations up to time k. And that restriction gives me a subspace. This is a closed subspace of, well, it's finite dimensional here, so everything's closed, but it's a subspace of this larger space L, the nonanticipativity subspace. And I can represent the nonanticipativity condition as being a condition that X should be in this smaller subspace. Now, as part of that subspace, there is its orthogonal complement, and this is where the idea of a multiplier will eventually enter. So I look at the orthogonal complement, but this is orthogonality with respect to this inner product, or the Euclidean inner product would give me something wrong for this idea. So the complementary subspace consists now of there are also functions obviously in the same space as Hilbert's space, but it's easy to calculate what they are. They are the functions such that they have a martingale-like condition that the expected value for the component at stage k, the expected value with respect to future information is 0. And so these are orthogonal to the other. If you know M, you get N, and so forth. This is usual kind of duality orthogonal subspaces. All right, now let's get into multistage stochastic optimization, which will be the model for multistage stochastic variational inequalities. So we're going to have other non-anticipativity is critical, but now we want some other constraints. So I'm going to look at, there could be many constraints, and I'll get to some more, even more complicated ones towards the end, but right now I just want to look at certain basic constraints which are just scenario by scenario. So I'm thinking here that for each scenario C, I have a set C of C, and I require the decision for that scenario to belong to that set. So these are conditions that are separated by scenario. And I'm going to now assume that those sets C of C are closed, convex, and non-empty, and that will mean that this set C, as a subset of this response space, is a closed convex set in that space. Remember, what am I doing? I'm building up the elements of a variational inequality. I'm going to have an underlying set. But at the moment, I'm just at the stage of optimization. So I'm interested in that, but now I'm going to also look at minimization of an expectation. So I'm going to look at a case where I have a convex function g, which is an expected value, and I'm going to minimize that over all response functions x that satisfy these constraints and are non-anticipative. So I'm going to minimize over the intersection of this set C and the subspace N. And just to make things work better for the talk, I'm going to assume that these functions, for each C, I have a smooth function. And that will mean that this expected function then will actually be a smooth function on my function space L. So, and then smooth, it has a gradient. How does that work out? Well, it has directional derivatives. It's easy to figure out what that would mean in the setting of the space L. And the gradient will be the element that, as an inner product, will give the directional derivative. And you can see that it turns out that this gradient, the gradient is again going to be a member of L. the gradient of a function on L will be a member of in the space L, and so it's a mapping that takes a scenario. In that case, it takes a scenario to the gradient with respect to that scenario. Gradient in X with respect to that scenario. And then if these functions are convex, I would have a convex function. So I'd be minimizing here a convex function over that intersection. So this would be a multi-stage stochastic programming problem. And what would be the first order optimality conditions for this? This is all pretty standard and elementary, except people are not accustomed to thinking about it in the setting of the response function space. So it comes out as minus the gradient as applied to the decision element X should belong to the normal cone to what? Of the set C intersect N, because that's the set we are minimizing over. This is the first order optimality condition. And if I have the convex case of this minimization problem, as is typical in stochastic programming, this would be a sufficient condition for that. So solving this, if I could solve this, this is a variational inequality. And it's a variational inequality involving gradient mapping. So if I can solve this for the decision X, which is presented here as a mapping, but it's really, you could think of it as a supervector in the right space, as I say. Then I have variation. I would be solving this problem. And so here's just a simple idea. If this is the case of a variational inequality standard in stochastic programming, why not put in place of that gradient mapping some other mapping, and then we would have what legitimately and rightfully should be called a stochastic variational inequality. But that is not a model that has been included in anything that has been in the literature that's called a stochastic variational inequality. People have focused mostly on one-stage things for which this does not fit. But this seems to me just naturally we must have a definition of a stochastic variational inequality that would include at least this. And could go beyond, but it must include at least this. And so what we're doing is, and if you look at the brown there previously, we were looking at the gradient of certain vectors. And now what we're doing is just taking some other mapping, F, which is a mapping from the space L into itself. And that means that the image of X as a function will be another function. And that image function is going to take C to the element F of X of C, which is an element of Rn. So that's the F of X is an element of the space L. And I'll assume that these functions are continuous. Again, you could get around all these things just for simplicity in the lecture. So then this would make F continuous. And so now we have what I would call a stochastic variational inequality in basic form. So minus this element should belong to the normal cone at this X. And what about monotonicity, if that's supposed to be so important? That comes in naturally here too. If each of these functions, little f, for each c I have a monotone function of x, then this f would be monotone in the space L. So that all fits very naturally. But this is what I call the basic form. Basic form because what I'm going to do is elaborate the cone structure, what does the normal cone mean? We can calculate what the normal cone means and translate this into something which is essentially equivalent but is much more productive to work with. I have a musical accompaniment here. That was a harp in heaven saying that I had made a good remark here. Okay, so we're looking at this variational inequality up there. And the question is how to understand this. So I had a picture at the beginning was some finite two-dimensional picture, but here we're dealing with some function space. So what does this mean? How can we understand this? And now you recall the set C is something about point scenario-wise constraints on the decision, and N was the nonanticipativity subspace. So if you apply a constraint qualification, a simple constraint qualification of convex analysis, or you could avoid it if the sets C of C are polyhedral or something, or various things, then you can show that then there's some little calculus. The normal cone to the intersection is the sum of the normal cones. And the normal cone to the non-anticipativity space just is always the complementary space, M. And on the other hand, with this NC, the vectors that are in the normal cone to that are just the ones that satisfy a pointwise condition. So by taking that thing and applying those rules, we can translate the stochastic variational inequality in basic form into one that I call extensive form, which looks like this. I'm looking for a response function x, which is non-anticipative, and is such that there exists another function, w, which is in this complementary or multiplier space, such that, and here's the dramatic part, that I have a separate condition for each scenario. There's no linkage in the remaining part. So I've gotten rid of the n. Basically, I've replaced the n, the non-anticipativity space n, by a multiplier, w, and reduced to a pointwise condition. And now these are essentially equivalent. So to go from the basic one to this one, you need a constraint qualification of some kind, probably, usually. But to go from this one to the other, you don't need anything. So if you solve this, you will automatically solve the other one. So for our purposes, we can really focus mostly on this. We're going to be interested in how you might solve this. So let's just worry about solving this. The idea of the constraint qualification is a small technical detail that doesn't need to bother us. So what does this condition mean then again? We got the variational inequality down to here, but what does it mean in the case of the stochastic programming model? It means something that has been understood for a long time, since the 1970s in stochastic optimization, that these vectors W give the thing that are called information prices. So if I take down here now that this f is the gradient in x, and then I see that this condition here, this pointwise condition, simply means that for each c, the x of c minimizes a function over c of c, which is not just the original objective, but the objective plus a linear term. And this linear term gives, the objective was already a cost, and this gives a cost of information, as we say. Roger Wetz, my longtime colleague in working on this kind of subject, is very fond of the cost of information and has employed it in many situations. It's the shadow price of information, much in the sense that Lagrange multipliers give shadow prices for constraints in optimization. You must all be familiar with that in some sense. It's the price at which you'd be willing to pay for a little bit extra. And so it has to do here with adjusting your decisions so it doesn't have to be non-anticipative. And this would free it up from that. And now, since we're aiming at getting a structure for which we can compute, we have to look more closely at these two subspaces, which are the foundation of this whole framework. And we're going to need to aggregate scenarios, put scenarios together in a certain way. We called it scenario aggregation in the original paper, which has to do with projection. So if I have these two spaces which are orthogonal to each other, I can take any element and project it onto both subspaces. And by the way, then I get a unique representation of that element as a sum in the two of elements in the two subspaces, orthogonal subspaces. But again, this orthogonality depends on my choice of the inner product. And I've chosen the expectation inner product because it makes a very nice result right here. So if I take P to be the projection onto the space N, then I minus P is the projection onto the complement. That's because of this thing about the thing being a sum of elements of the two projections. So here's how this works out, though. Can we execute this projection? We can execute it in the following way. We have to understand the idea of, this is where the aggregation is coming in actually. Scenarios at stage K, we can say, there are many ways you could express this, the two different scenarios are information equivalent if they have given the same observations up to this stage. At some later stages they may give different observations, but up to this stage K, This is at stage k, their information, if they've given the same information up to stage k. So this amounts to an equivalence class. And we are partitioning all the scenarios into the information that we have made available at stage k. I could also rewrite all this in the probabilistic theory of filters and so forth, but this is an easy way to see it since I'm in this finite setting. Basically, kind of a scenario tree setting that I've chosen here. So now I can, if I take a scenario, C, I can write down here A sub k of C as the equivalence class at stage k. It's all the scenarios that have given the same information up to stage k as has the scenario C. And then in terms of that, I can write what the projection is. So what am I going to project? I'm going to take a function x bar, I called it here, in the space L. I'm going to project x bar onto this n to get an x. And how will I get the x and n, that is the projection of x bar? It's basically I get it by taking conditional expectations. Here's a formula. X k of c is a certain ratio of two sums. And the sum at the bottom in the denominator, you can see, is simply the probability associated with that equivalence class. And I'm dividing, and then I'm taking this sum here, so I'm dividing. It's essentially, I'm just giving the conditional expectation over that equivalence class, and this is this aggregation operator, and then I get this decision, CK. So this is really easy to compute. A very simple linear operation that has many known properties. Now I come to an algorithm that Roger and Wetz and I developed back in 1991. Actually, it was interesting. We were making our first visit to China. We were in Beijing in 1986, and Roger raised the issue about how something that what a lot of people do doing in those days anyway, when they had uncertainty in a complicated setting, even with many time periods, they would say, do a lot of things with hindsight. They would say, let we take a scenario. Suppose this happened 1, 2, 3, 4, 5, 6, and the whole scenario. What if this scenario happened? And then deterministically, they would calculate what an optimal solution would be or something for this thing if you knew the whole scenario. And they would do this for a number of scenarios. And then they would get these results, what's optimal for each of these separate scenarios. But then what? Then what should you do? Take an average? What should you do with this? How should you combine these? And so we started to think about how to make this work, and eventually we found how to make it work in terms of the proximal point algorithm and this kind of setting. And this is what we came up with in that way. And this is a statement that involves a positive parameter, as does the proximal point algorithm. But in the proximal point algorithm, if you're familiar with that, you know exactly what will happen as the parameter gets too big or too little or something like that. But this parameter, it's not very clear what it should be. This is one of the drawbacks of the algorithm. If it's too low, the algorithm might be too slow. If it's too high, it might be too slow. Where's the happy medium? It's not so clear. And I'm personally not one who's worked with this very much, but Roger Wetz has worked with it a lot, and David Woodruff has done lots of work implementing it, and they apparently are having a lot of success for even non-convex in the sense of mixed integer programming, and they use it for getting bounds. So and I don't know, these people claim it works really well, but I'm not the one to report so much on this. I'm just the theoretician about this method. So here's how it works. At any given stage, it's elementary to initiate it. We don't have to talk about that necessarily. At every given stage, and I follow Roger and always liking nu for the index for a sequence. So I have an x nu, which is a non-anticipative decision. And I have a w nu, which is in this multiplier space. And I'm going to construct an x bar nu, but this will only be an L, not an N. X bar nu will only be in the big space. And I'm going to do it by solving a separate problem for each scenario. This is like what people were doing in solving. They take a scenario and solve a whole optimization problem for that scenario. But the scenario problem here is modified in two ways. It's modified in that it has this information price term with a W. That's one way. And it's modified in another way that has a proximal term. the decision you're looking at should not be too far from the x nu that you already had from the function in L. So it's a mixture of information prices and proximal terms. But of course, I revealed the secret. This is based on the proximal point algorithm, so it's not surprising that proximal terms are in there. But you don't see a term in W, for example. All right, now, then after you have solved that for each C, that way you've gotten a function in L, because you have computed separately its value for each scenario C. And now we're going to get the update of our x and w, and the x will be an n, and the updated w will be an m, and we do this by this aggregation, which is a term we're using for this projection. So we take this larger element, and now we project it on the nonanticipativity subspace. That's the operation involving conditional expectations. And then we update the multiplier by a sort of what a lot of people recognize as a sort of augmented Lagrangian-like update, and so forth. And now, well, will this work? Well, what I haven't written on the slide, I have to get to, I'm going to say more about this later. I shouldn't have written it this way without saying if this is, well, okay, no, that's okay. This is the convex case. So right now, I said I could be looking at it, but I'm looking at the convex case of stochastic programming. That's right. The convex case of stochastic programming, it will always converge. I'm looking here at the pure version with exact minimization at each step. No matter where you start, you'll have a sequence that not only it converges to some particular element. Even if the solution to the problem is not unique, it will converge to a particular element. This is another clue that the proximal point algorithm is involved, because it's practically the only algorithm I know which has this type of property. And it does so in a way that you can see the effect of the parameter r. It does so in a way that the distances are reduced not in a sort of Euclidean norm, but in terms of a norm where I have the distance between the x's is being evaluated differently than the distance between the y's, which has this multiplier 1 over r squared. So for example, if r is very big, then that is weakening the amount of the sense in which the multipliers will converge. But if it's very small, then the opposite will happen. It'll weaken the senses. So some sort of trade-off, and this trade-off is a bit troublesome for the implementation of the algorithm, because it has to be somehow developed through experience, and people say they have done that. Okay, now what do we do about progressive hedging? So progressive hedging, we have something very similar. We're looking for an x in the n space and a w in the m space, such that a certain pointwise condition is satisfied at every iteration. All we need to do to see what the algorithm should be for this is to translate the optimization algorithm into a statement about gradients. Well, how that optimization problem would apply if you looked at it in gradients, and this is what it is. So again, having an x nu in the n space, a w nu in that space, we get an x bar nu, which is in the larger space, not non-anticipative, by solving for each scenario a modified variational inequality where the modification is I replace the f by this f nu. This f nu has, I'm adding the w nu, that's corresponding to the linear term in stochastics, and I'm adding this r times the difference. That's what corresponds in gradients to the quadratic term, the proximal term that was in stochastic. All right? And then after I have solved that for each two, then I have I do the same thing again. So I project onto the two space, onto that space. That's again this same rule, and then I have this update rule for the multipliers, and get the same convergence result. But it does say here in the monotone case. So for this convergence result here, I have to have the mapping be monotone, but I have more to say about this. This is where we just want to use the argument as it's already given for progressive hedging and just translate it with just this simple scheme. Just translate from optimization into a statement about gradients and then generalize to some other mapping. And you'll get exactly the same convergence. Now I should say too, in the case of progressive hedging in stochastic programming, there are all kinds of other things you can say. You don't have to do exact minimization. There's some way of stopping bounds, or also there's ways of developing linear convergence. All these things are pretty well known. You just can translate them out of the theory of the proximal point algorithm, and there's no need to present all those somewhat unpleasant looking little details, and because it's all there. But the idea is that whole concept goes. So okay, now what is it? As I say, this is based on the proximal point algorithm, but it's not the proximal point algorithm applied to anything you see directly in the statement of the problem. You set up a certain mapping, and you take something called the partial inverse of that mapping. You invert it in some variables, but not in others. In effect, you're passing from a sort of a primal variational inequality to a kind of primal dual variational inequality. But the primal dual is dictated by the two spaces n and m, sort of a skew or a twist, a change of coordinates to get it. So in that basic context, then if you wanted this global convergence, you should ask for this mapping, not one of the direct ones. This mapping should be maximum monotone. And in the case of stochastic programming or the monotone case of the stochastic variational inequality, it will be. So then all those results would hold. But could it just converge locally? There are some results about local convergence of proximal point algorithm. And Bernard Swider with Teemu Penn and so on, they have various conditions about getting it locally. And I haven't studied exactly their proof, but it's a pretty easy way to see why the thing would work locally. But you have to be careful what you mean by local. What you mean by local is looking at the graph of a maximal monotone mapping and looking at a neighborhood of a point in the graph, because the mapping might not be single valued or anything. You have to look at the locality in the graphical sense here. So as long as you have that maximal monotone relative some neighborhood of the solution as it translates into this mapping T, then you will get global that current. Okay, but I've actually gone a lot further than this with my thinking and the things I've been writing down, but are not yet put into a paper that's paper is not finished yet for being published. For one is that you don't necessarily, if you're talking about stochastic programming, you don't necessarily require convexity, because it's possible that you can use, well, I'm convinced you can use second order optimality conditions at the solution and show that they will create, if you do things right, they will create a sort of a local convexity and monotonicity that will make the algorithm work. Another thing is that you can apply this algorithm. This is a topic I'll talk about in Buzios. You can just go back to the progressive hedging for stochastic programming. You can replace the expected value by a risk measure and still translate it into this phase where you could use the progressive hedging algorithm to solve it. And then, of course, we want to go beyond just optimization. One of the big motivations for stochastic variational inequalities is that you want to solve game models and equilibrium models, competitive models. So imagine, for example, that we have a game version in which you have different players and each one is solving a multistage stochastic optimization problem, but they are somehow interacting. And we can set this up. We could write down optimality conditions for that, following a pattern I gave earlier, and then you would get some sort of some version of it would fit this pattern, a stochastic variational inequality, and we would want to solve that. But one of the troubles is those equilibrium problems are almost never monotone. Non-monotone, and globally anyway, monotonicity comes up. Now, they exhibit local monotonicity if in your game the actions of the other players are damped down enough there, and they're not so large as to overwhelm the player. They can influence but not overwhelm the player. Then you could show you have monotonicity around a solution. But I believe that there's another way, that there's a technique I call elicitation of monotonicity, which is related to augmented Lagrangians, in which, under certain circumstances, we can create this kind of monotonicity. So I think all of this stuff can be worked out in games eventually, and quite a good picture there. And here would be an example then of such a game. I have, for each agent, I have an agent is going to solve an optimization problem here with a response function xj, and it'll involve underlying set cj for each scenario. And there will be nonanticipativity for that agent. And then there will be costs associated with it, and those costs are taking a traditional approach. We can also work with an extended game, for example, but the costs can depend on what the other player is doing, x minus j for that. And then the agent is going to try to minimize here an expected cost. But we should be able to do risk measure, and we can. We could do that too. But here it's just an expected cost, and it's over some over such an intersection set and so forth. And we have first order optimality. And then following that basic pattern, you can go back and put it all together again as minimizing, well, as a single stochastic variational inequality. And again, there will be this multiplier space, and there will be all this decomposition. So all of that is going to work. That doesn't depend on monotonicity. That just depends on the calculus of normal cones. The question of the algorithm, though, depends on what degree of monotonicity you will be able to find or elicit in the problem. And I think that subject has much more potential than anybody has really dreamed about. There's so many ways to do that, but it's going to be local. So how local? This is a bugaboo of all these things which are just local, but so much nonlinear optimization. If you're near enough to a solution, something will work. But how do you know you're near enough? So nothing is going to be perfect in all of this. But also in here you can see that when you get into these games, you're going to get into some other possibilities. Maybe the information isn't going to be the same for every player. So you have to try to, maybe the scenario, the way the scenarios and the observations are different. So there could be a lot of extra things. It's a big topic people could work on. So much could be done there. And so here was the idea again about minimizing a risk measure in one version. I'll be more explicit about it in Buzios, but suppose we have conditional value at risk. There's a particular measure of risk, and now I'm not in the game setting anymore. I'm just looking at an optimization setting in which I've replaced minimizing the expected value to minimizing a C-var value at a given alpha, and then there's a certain formula for here. And in terms of this formula, you can set up a certain kind of Lagrangian. And then you could write the optimality conditions as a Lagrangian stochastic variational inequality, and get one in a terminal in which you'd have an x of z of c as a terminal decision. So anyway, there are possibilities. This is one way. I'm going to show you actually quite a different way in Buzios of doing that. So anyway, it's a way to integrate that all into the same picture. I'm almost done. I have some rather complicated slides, which I'll just give you some basic ideas. Some of you saw this in the talk yesterday. Just want to remind you that when we look at a basic constraint, like x of c belongs to a set c of c, but that set is given by a system of constraints, then there's a calculus rule for the normal cone, which may depend on a constraint qualification. If this D is a cone and its polar is y, then you get some way of calculating the things, and so then you will get expand your problem into a representation in which multipliers will come in. So, and there's some way that it still fits as a stochastic variational inequality in basic form. Another thing you could consider is constraints beyond basic constraints. For example, some expected constraints, but again, they could also be risk constraints eventually. All this would work in. I'm just in my final minutes explaining that the core model I described can be elaborated in many ways to include other features. So here's a case where this other system of constraints could be introduced. You could introduce some more multipliers and somehow just play around with that, and you could work it down into, now I have a variational inequality which is not over C intersect n but K intersect n, and there's a way to work it all out and where I fit it all back into the same pattern eventually. So that's all I'm talking about in a technical way, and then here are some references. This is the paper that Wetz and I have written, and it's already accepted and it's published online, but I don't know how to access it on Springer. I look on the Springer website and I can't figure out any way, and if you do mathematical programming B, you only come up with mathematical programming A, so I don't know what to do about that, but you could download it from my website, this paper. And then I just remind you of two historical things here, that this progressive hedging algorithm came from this work that Roger and I did in 1991, and the whole idea of looking at nonanticipativity as a constraint in a space of response functions goes back even earlier in the theory of stochastic programming. Okay, that's all. Thank you.